Good day, folks. Today we're going to take a look at the imaginary number system. And our note today is to define and use imaginary and complex numbers. And when you're all done today, you will be able to do a problem much like what you see right here. Yes, we'll be able to solve that and get a complex solution. By the way, in your notes, go ahead and write down the wicker know and do and the essential question here as well. All right, go ahead and pause it and get that information down in your notes. Let's take a second and simplify these radicals. Now, just to review a little bit, the square root of 16, remember what you need to do. You remember those perfect squares? 2 squared is 4. Okay, 3 squared is 9. 4 squared is 16. 5 squared, 25, so on and so forth. Okay, so we ask ourselves, will any of these go into 16? Well, yes, of course, 16 does. And it turns out the square root of 16, of course, is 4. All right, now, looking to the next one, we ask ourselves, what is the largest perfect square that goes into 8? Well, 4 does, and 4 goes into it twice. So we have the square root of 4 times 2, or you can write it square root of 4 times square root of 2. Square root of 4 is 2, and you bring down the radical 2, and now that is simplified. All right, one more. Let's just review one more here. You have 27. What's the largest perfect square that goes into 27? Well, you can play with your calculator and try to figure it out, or you may know it's 9 right here. Okay, so it's going to be square root of 9 times 3. And of course, square root of 9 times the square root of 3, that'll give you 3 times the square root of 3. All right, so that's enough review for today. Let's get into the lesson. In class, we talked about a problem similar to this one. If I have f of x is equal to x squared plus 1 right here. And if I were to graph it, it would look like what I have right here. Now, does that graph come down and touch the x-axis? Well, no, it doesn't. Okay, and because it doesn't, that means it doesn't have any zeros. Okay, now look why it doesn't have any zeros. If I were to take this, set it equal to 0, subtract the 1 to both sides, so let's go ahead and do that. X squared equals negative 1. We take the square root of both sides like this, and I get x is equal to plus or minus the square root of negative 1. Now, how do I handle that? Well, we've also discussed the idea of a discriminant. What happens when you have a number less than 0 as a discriminant? Well, yes, it has no real solutions. And of course, as we discussed in class briefly, the imaginary number system is born. Okay, so we are going to let that square root of negative 1 be equal to the imaginary unit. And we're going to represent that imaginary unit with the letter I. Okay, now go ahead and pause this video and make sure you fill out the information on this slide on your note guide. On your Cornell note sheet, you are going to see a chart like what you see here. Now I want you to write this down so you filled it in. Okay, now but let's read through this. It says, an imaginary number is a square root of a negative number. Now, imaginary numbers can be written in the form of bi. Now notice, b is a real number, and the I is the imaginary unit. Now, what were to happen if I were to take the square of an imaginary number? Well, if I were to square an imaginary number, I would get the original negative number. Okay, so let's go back ahead and let's look at an example showing what this is. Okay, we know that right here, square root of negative 1 is I. We know that. Okay, now, if I take the square root of 2i, that's equal to the square root of 1 times 2. Square root of negative 1 times the square root of 2. Okay, shown here. And the square root of negative 1 is I, leaving me with I radical 2. Now, if I were to take this one, square root of negative 4, we can break that up. That's the square root of negative 1 times 4, okay, or the square root of negative 1 times the square root of 4. Now, the square root of negative 1 is I, square root of 4 is 2. Now, what happens if I square an imaginary number? If I square imaginary number, we have to first deal with this right here. Notice, if I have the square root of negative 1, that is I. and then I bring in that squared in, so I have an I squared. Now, what is an I squared times an I squared? Well, an I squared times an I squared is -1. Okay. All right, so that leads us to the square root of -1 squared gives me just -1. All right, now looking at the algebra. If b is a positive real number, then the square root of -b is equal to I times radical b. And if I were to have the square root of -b squared, okay, now, first of all, we need to take care of the negative. Square root of the negative is I, and the square root of b squared is b. Now, if we go backwards with it, I have the square root. Now, I want you to see something here. I want you to notice something. Over here, the square undoes the radical, leaving you with the radicand. Likewise, this square undoes this radical right here, leaving me with this radicand. And that's how we get -b. All right, go ahead and pause this and get all this down. Okay, let's take a look at a problem here. I have 5 times the square root of -121. Now, first thing I want to do is I want to break it up, and I want to break it up so I have 5 times the square root of -1 times 121. Now, we're going to go an extra step, and it's going to be 5 times the square root of -1 times the square root of 121. Okay, so let's uncover a few of these things. All right, okay, so there, it's done that way, just like what we showed right here. Okay, now I'm going to take the square root of both of those. Okay, so now I have the square root of -1 and the square root of 121. Now, does 121 have a perfect square? 121 is a perfect square. And of course, the square root of -1 is known as, you said it, it's I. Okay, so let's go ahead and uncover this. So now I have 5 times 11. And of course, the square root of -1 is going to be I, leaving me with 55I. All right, go ahead and pause the video, make sure you got this down, and then we'll go on to the next problem. Okay, let's see if we can describe this in terms of I. So I'd like you to pause the video, see if you can work it, and then we'll work it together. So go ahead and pause it. Okay, now that you've done this, let's work this together. So looking at this one here, that gives me the square root of -1 times 12, which is the same as the square root of -1 times the square root of 12. Now, is there a perfect square in 12? Well, yes, there was. What is it? Well, 4. So now I get the square root of -1 times the square root of 4 times 3. Now, I'm going to break that radical up a little bit more so it becomes square root of 4 times the square root of 3. Now, we know that the square root of -1 is going to be I. We know that the square root of 4 is 2. So I'm going to write it as 2I times the square root of 3. Okay, let's see if we agree. And do we agree? Yes, we do. Okay, let's go try another. Okay, looking at this one, notice there's a number on the outside of it. Okay, and looking here, I have -1 times 36. Now, 36 is a perfect square. So I can go ahead and take square root of -1 times square root of 36. Now the square root of 36 is going to be, you said it, 6. So now I have 2 times 6. And the square root of -1 is I. Now just multiply the 2 and the 6 together, and we will get 12I. And let's check to see how we did. Did we agree? And yes, we did. Okay, now let's take a look at a problem where we can use some of the skills that we've been looking at. So, first of all, let's ask ourselves, if I have x squared is equal to -124, what do I do to solve for x? Well, if you said take the square root of both sides, you are correct. And if you take the square root of both sides, you're going to get this. So x is equal to plus or minus the square root of -144. Now remember, that is equal to, so x is equal to plus or minus the square root of -1 times 144, which we can break up to be plus or minus the square root of -1 times the square root of 144. And is there a perfect square in 144? Well, yes, 144 is a perfect square. So what does that mean for us? Well, that simply means that you can take the square root of -1, which is I, and the square root of 144, which is 12. Yes, so our answer is plus or minus 12i. Now, for this next problem, I want you to take a look at this. See, it's 5x squared plus 90 equals 0. Now, of course, you could solve this using any of the other 5 methods, but I'm going to show you a trick. Well, it's not really a trick, but it's a technique that can be used when I don't have a linear term. You see how we don't have a plus 0x? If you don't have a linear term, we can do a process that is called extracting the root. In other words, I want to get this x squared by itself. I can do that by subtracting 90 to both sides. Now, after I subtract 90 to both sides, you have 5x squared is equal to negative 90. Now, you can divide by 5 on both sides, and you get x squared is equal to 18. Okay, so let's put an 18 there. Now, at this point, we can take, don't forget the negative, it's negative 18. So we can take the square root of both sides, and I get x is equal to plus or minus square root of negative 18. Now at this point, you just simplify for it. So remember, 18 is what? Let's go over here and write this. So it's going to be negative 1. And is there a perfect square in 18? Well, yes, 9 times 2. Okay, so that gives us square root of negative 1 times the square root of 9 times the square root of 2. And then we can see that x is going to be equal to 3i times the square root of 2. It's going to be plus or minus, and then of course, don't forget, put it in set builder notation. Alright, and that's how you do that problem. Alright, in your notes you're going to see a place where you can put the definition for a complex number. Okay, now a complex number is a number that can be written in this form, a plus bi. Now, a and b are going to be real numbers. Okay. However, let's go down here and look. You have a real part, which is the a right here. That's the real part. And you have an imaginary part. Okay. That's this part right here. Now, when you put the real part plus the imaginary part together, you have a complex number system. Okay. And then let's go back up here and notice it says the set of real numbers is a subset of the set of complex numbers. Okay, so what that means is since I have a real part, here's my real numbers, here's my imaginary numbers, and you put them together, and both of these subsets, or should I say both of these sets, are subsets of the whole thing. So the complex number system. So go ahead and pause and get this slide down in your notes. Now, let me explain a little bit further. I want you to know that real numbers are complex numbers where the b value is equal to 0. And imaginary numbers are complex numbers where the a value is equal to 0. And of course, the b value cannot equal to 0. So these are sometimes called the pure imaginary numbers. Now, what am I saying when I say these? Well, if I have just a bi, and whatever that b value is, anything other than 0, then this is called a pure imaginary number. Now, let's talk about when two complex numbers are going to be equal. Two complex numbers are equal if and only if this a value is the same as this c value right here, and this b value here is equal to this d value there. So if a is equal to c and b is equal to d, then we say that these two complex numbers are equal. Now in your homework tonight, you're going to see a few problems like this. And now I didn't leave a spot in your notes where you can write this down, so you may want to squeeze it in maybe to the left in that little margin area. But the question here says, find the value of x and y that make the equation true. So you're going to use the idea of the quality of complex numbers to solve for this. Now, you know that if they are equal, that means these two parts are going to be equal. So you can simply set 4x equal to 2. And likewise, you can set the imaginary parts, and make sure you get the negative in there, equal to 0 as well. Now, you don't need to put the I there, okay? And that's what I did right here. And then we can just solve in both cases, and I find that x equals a half, and y equals negative 5/2. Okay, let's put this all together, and let's find the zeros of functions. Okay, I have a zero, or I have a function, and I want to find the zeros of this function. Okay, so now notice it has a linear term. So when it has a linear term, we are just simply going to, well, let's just complete the square on it. Let's do it that way here. Now, could I use the quadratic formula? You betcha I could. But in this one here, I'm going to complete the square. Okay, so to start out with, we set it equal to 0. Okay? Then, after you do that, then we need to rewrite it by, well, first of all, ask yourself, is there an a value right here that we can divide everything by? And the answer is no. Okay, so we're going to subtract 26 to both sides. Okay, and we put in our little box area there. Okay, then I'm going to take half of the linear term. Half of 10 is 5. You're going to square it, and then we're going to add that to both sides. Now, simplifying that, that's going to give us this right here. So, now we're going to take the square root of both sides. So, we're going to take the square root of this side, square root of this side, and that will give me x plus a 5 is equal to plus or minus negative 1. Now, remember what negative 1 is. This is I, okay? So, but I need to get this x by itself. So I'm going to do that by subtracting 5 to both sides. And when I subtract 5 to both sides, you're going to get x is equal to 5 plus or minus, and let's replace that square root of negative 1 with an I, and we end up with that answer right there. And notice what that is. It is a complex number. Why? Because it has a real part and an imaginary part. Let's go ahead and try this one. So I want you to pause it, and I want you to see if you can work through this one. And then when you're done, we'll hit play again, and we'll look at it together. Okay, so go ahead and pause the video here. Okay, now that you've done this, let's see how you've done. Okay, so first of all, we set it equal to 0. So we have x squared plus a 4x plus a 12, set it equal to 0. Okay, now, is there an a value other than 1? No. Okay, so I'm going to subtract this 12 over to this side. And that gives us x squared plus a 4x plus a box is equal to negative 12, and I'm going to put plus my box there. Okay, we're going to take half of this linear term. Half of that linear term is 2. Okay, so let me write it over here. And then we're going to square that. So 4 divided by 2 is 2. 2 squared is 4. So I'm going to add a 4 to both sides, just like that. Now, simplifying this, I have x squared plus a 4x plus a 4 is equal to a negative 8. All right, now, let's factor it. So I know it's going to come up with x plus a 2, the quantity squared, equals negative 8. Now, we're going to take the square root of both sides, just like that. And I'm left with x plus a 2 is equal to plus or minus square root of negative 8. Lastly, I'm going to subtract 2 to both sides, and I will get x is equal to negative 2 plus or minus the square root of negative 8. Okay, now remember, let's go up here, and the square root of negative 8 is equal to the square root of negative 1 times, now is there a perfect square in 8? Yes, 4 times 2. Okay, so that gives us the square root of negative 1 times the square root of 4 times the square root of 2, which will give me, now the square root of negative 1 is I, the square root of 4 is 2, and I'm left with the square root of 2. And that leaves us what our answer is going to be, and here it is, all simplified down. Okay, now, at that point, remember, put it in set builder notation, And there you go. We've done it. Now let's take a look at a possible solution to a problem that we could work. I want you to notice in each case we had the real part plus or minus to the imaginary part. In every case we had plus or minus. Well, this here and this here, there's a name between these two. They're called complex conjugates. So in your notes I want you to write down complex conjugate. Matter of fact, they are a complex conjugate pair. Now, this leads us to something. If I have this real number right here, or I'm sorry, this complex number right here, if I have a plus bi, you know that we're also going to have its complex conjugate, which would be a minus bi. Okay, so I want you to realize, in identifying roots, if you have one of them, you know the other one is hanging around there someplace. Okay, so this leads us to this statement. If a quadratic equation with real coefficients has non-real roots, then those roots will always be complex conjugates of each other. Okay, so let me say that again. If a quadratic equation with real coefficients has non-real roots, then those roots are called complex conjugates. All right, let's move on. So let's apply what we've just learned. And I want you to find the complex conjugate. So here we go. I have complex roots here. It's 8 plus 5i. So I know that its complex conjugate is also going to be root. So what is the complex conjugate of 8 plus 5i? Well, 8 minus 5i. Okay, now here's another one, 6i. Now remember that's the same as 0 plus 6i. Okay, so what's the complex conjugate of 0 plus 6i? It'd be 0 minus 6i, which means the complex conjugate is simply negative 6i. Okay guys, well that gives it a wrap for today. Here is your assignment, and we're going to work on this in class next class period. So go ahead and write this in your notes, and we'll work on it when we come to class. Have a great day, and adios.